Hi Apurva, kindly unmute yourself.
Sorry, Di, I forgot. Sorry. Hello everyone. Welcome to today's speaker session of GDSC Banasthali Vidyapith. This is Apurva Kaushal, a team member of GDSC Banasthali Vidyapith. A huge thank you to our audience for awaiting this session and joining us today. If this is indeed your very first time attending a GDSC event, let me guide you through GDSC. Google Developer Student Clubs or college communities run by students who encourage peers for building a collaborative environment that has the potential to generate solutions to real-world problems. And GDSC Banasthali Vidyapith is one among them. With that being said, we take immense pride in introducing our guest speaker for today's session, Mr. ARPIT SARDANA sir, who is a software developer at Flipkart. He has been to ACM-ICPC Regionals twice, that is in his second year and in his fourth year. We are glad to have you here with us, sir. Now, moving on to today's agenda, we'll have an overview of trees and graphs. We'll be able to understand the techniques to solve questions, and at the end of this session, you will be able to ace the topic using exclusive tips and tricks. Now, without further ado, let's start with our session today on trees and graphs. If you have any doubt, you may drop them in the comment section. We'll take them in the end. Over to you, sir.
Hi, folks. It's good to join you all. So as Apurva already went through my introduction, this is Arpit. I'm working as a software developer at Flipkart, and I've been to ACM-ICPC Regionals twice. So today we'll just be covering trees and graphs. And obviously, since the session is just 1 hour, we can't really dive into the topics, right? So I'll just try to cover some of the things and give an overview of like some of the most asked questions. And then obviously, if you have some doubts, feel free to ask me, and then we can dive deeper into some of the questions. So, okay. I'll just share my screen so that you can see. Okay. So again, first we'll just start off with trees. So as you all probably already know, trees are hierarchical data structures, and I think before jumping into trees, the only data structures that we actually sort of know are your strings, your arrays, your stacks and queues. So these are all basically linear data structure. So trees is technical the first hierarchical data structure that we see. So what I mean by hierarchical data structure is, we'll just say, for example, take an example of the of an organizational structure where, let's just suppose I am an employee, and then obviously my manager has several employees under him. So it's like a one-to-many relationship. So these are basically n-array trees. This relationship can be depicted as an n-array trees. So it's, as it's already written, trees are undirected, connected, and acyclic graphs. So obviously there isn't really any direction in the trees. They are just one edge, and everything just has a parent-child relationship, and every node is connected to a parent. And yep. So there are like several types of trees that you must have heard of or you have seen. So these are the n-ary trees. So n-ary trees, as I already said, is when a particular node has several children. So it can have n number of children, and again, these children could have n number of children. So there can be a lot of nodes over here. And one thing that I also like to emphasize about the trees is basically if, in a tree with n vertices, there will always be n minus one edges, right? Because there is just one edge connecting two particular nodes. And then I think we have the binary trees, which are probably the most asked in you can say your interview questions or things like that. They are the most popular ones. And then again, in binary trees, we have BSTs, AVL, red, black, and segment trees. So BSTs are just binary trees which have a particular order or how they are sorted. We'll just go into it deeper. And AVL and red, black trees are basically your BSTs, which are height dependent. So again, the number of nodes are over here are just if a tree has n number of nodes in AVL and red black trees, the average number of time complexity or average the height of the tree would basically be of the order of O log n. And then we have the segment trees. Again, segment trees are something that we often see in competitive programming, and they're trees that helps us solve range-bound questions. So again, it's a huge topic. So for the course of for this particular session, we'll just ignore AVL red black because they aren't really asked by anyone, and segment is a whole another topic. So it doesn't really make sense to go into there. Okay. Okay, before also starting the session, let me know if you have any concerns or if I went through a particular thing too fast or you weren't able to get it. So again, so that we can actually go through it deeper, and I can try to give an overview of what I actually meant. Wait, I think first I'll just stop my screen so that okay. So first off, we have the binary trees. So again, in binary trees, we have a particular parent or a particular node would just have at most two children, which are generally referred to as a left child and a right child. For example, in the tree that I have shown in front of you, one of the node is the node with a value 5, and it has one left node, which is 2, and one right node, which is 3. And generally, the top node, if we are going through terminologies, the top node is generally referred to as the root. So in this particular case, 5 is your root, and then there are leaf nodes. So leaf nodes are basically nodes which don't really have any children. So taking the example of this particular case, leaf nodes are 7, 4, and 6. Because as you can see, 7 doesn't really have any children, and neither do 4 and 6. And then we have the sibling. So a sibling basically means that they share a common parent. So if I have to tell you what the sibling of 2 would be, it would be 3, because again, 2 and 3 have a similar parent, which is 5. And then we have ancestors. So ancestors are basically your parents, and things like that. So taking the example of node 1 over here, our ancestors would be 2, 5, and for example of 6, it would be 3 and 5. So generally, a binary tree is referred to in this structure. So it has some sort of data attached to a particular node, which, as you can see, I've already labeled some of the data. And then we have a left node and a right node. And so what we'll actually do is we'll actually start off with how we actually make a tree, and then we'll cover some of the traversals techniques, because trees is basically just understanding what sort of a traversal you need to know and just recursion. So if you understand that, then basically all of the almost 95% of questions you'll be able to solve if you just understand the basics of recursions and are able to gauge what sort of an traversal that you need to do for a particular questions. And then we'll just cover some of the questions like height of a tree, how to calculate it, and sum of all nodes and diameter. I mean, I'll try to cover it, but if it extends, obviously we might have to cut some of these short. So yeah, let's just start with the traversals. So we have three types of traversals. We have actually two types of traversals. One is the level order, and the other is other hierarchy. So these are the pre-order traversal, the in-order traversal, and the post-order traversal. So what happens in a pre-order traversal is when we are actually at a particular node. So, for example, if we are at the node 5, what we do is we just print whatever the data of the node is, and then we go to the left node. And again, when we are at the node, let's say 2, then we'll first print its data, and then again, first we print data, then we go to the left, then we go to the right. So if we were to go over what would the pre-order traversal of this particular tree would be, again, let's just say first we are at the root node, obviously. So we'll print the data, so that is 5. And then we'll go to the left subtree. So that is the node 2. And for every single node, we have to carry the operation in this order, which is the data left and right. So when we are at the node 2, we'll again do the operation in the same order. So first is the data. So again, we do 2, and then we go to the left. So again, we go to the left subtree of 2, which is the subtree with 1 and 7. So again, we follow the same order, which is first we say 1. And after printing the data, we see that there is obviously no left subtree in 3, right? It's just null. So we'll just ignore that and move to the other part. So that is the right part. So then we go to the node 7 and we print 7, and we again follow the same operations, data left and right. So data is 7, and we don't really have any left or right over there. So we just print that data. And then you'll just go up the order. It's basically in a recursion. So you see that we have already covered the data left and right of the node 7. We have already covered covered all the operations on node 1, but we haven't really covered the operations on node 2. So for the node 2, we have already only seen that that we have printed the data and we have covered the left subtree. We haven't really covered the right subtree. So obviously we have to go over there. So we go on to the right subtree of 2, which is 4. So we print that data, and then you see that we have covered the node 5 and all of its left subtree, but we haven't covered its right subtree. So we follow the same operations, and going over the same operations, we get the traversal as this. And in order, it's just another variation of one of these traversals, one of these 3 traversals, which is instead of printing the data first, we actually go to the left subtree first, and then we print the data, and then we go to the right. So and taking this particular examples, we'll keep going towards the left. So we have 1, and then we'll just obviously at the node 1 we can't really go any more left, so we'll just print the data, and then after that we'll go right. So this is this, and again this is basically how we cover all the traversal. And post order, I think you can already infer that post order traversal is just going to the left and then going to the right, and then printing the data. So post order traversal is also sort of sometimes known as the bottom up traversal. So let's just go over to the programs, some of the codes of this. So again, for printing the pre-order, basically we have the root node, and we just obviously check recursion base case that if the root is null, we'll just return from our recursion, and then we do the pre-order in the order that we have decided. So obviously in the pre-order, we can see that first we have to go to the data, then first we have to print the data, then we have to go to the left subtree, and then we have to go to the right subtree. So this is what's happening over here. We first are printing the data, then we are going to the left subtree, and then we are going to the right subtree. So if you were to also write the code of the in-order traversal, and in order, it would be like obviously in between pre-order and in-order, you can see that the difference is that we are in pre-order, we are just printing the data and then going to the left subtree. In order, we are first going to the left subtree and then printing the data. So we just have to switch over these lines, and we'll have our answer. And again, for yeah. And then we'll just print for the post order. So as you can see in post order, first we go to the left subtree, then we go to the right subtree, and then we print the data. So again, just switch over these statements, and we have our post order traversal. So this is all for the pre-order, in order, and the post-order traversal. And the next sort of traversal that we have is the level order traversal. So what happens in a level order traversal is basically we print all of these nodes in a particular level. So first we'll cover the nodes at the level 0, which is 5. So if I can just... So what the order would be is, would be, again, as you can see, first it will be 5, then we have 2, then we have 3, then we have 4, then we have 4, 1, 4, 6, and 7. So as you can see, we first print the all the nodes at the level 0, then we go on to the level 1, then we go on to the level 2, and then finally we go on to the level 3. So this was for the level order traversal. So generally when we have to, so again, you can see that this is sort of similar to we are actually covering these nodes in a breadth first search, right? So generally what we do in this question is, it just implicitly what just comes to you is that we have to use some sort of queue. So again, to do this sort of a travel, we'll actually use a queue. So what we will do is, so just assume we have the root, which is, I'll just write a code quickly for it. I mean, just pseudocode. So again, so what we do is we'll just create a queue. So let's just assume we have created a queue, and then we'll just push the first node, which is the root. So again, the queue would obviously be of the type node star, because we're actually pushing the nodes in it. So so this is our queue, and then what we do is, while not a queue or empty. Okay, maybe I'll just write it in. Okay, so I'll just go through what is happening in each line later. So what I'm just doing is just printing the basic logic of what we are doing. So so what is happening is, what we are doing is actually we'll just obviously we push the first node in our queue. So we push the node 5, and what we do is just see that if the queue is not empty. So if the queue is not empty, we just take the topmost node out. So as you can see, our queue just contains the node 5 right now. So we'll take it out and just push both of its children. So we have till now what we have printed 5, and then our queue is 5, but we have already popped it, right? So now we have now we'll push both of its children. So now we'll have 2 and 3, and again we go on to our while loop and see if the queue is not empty. So right now queue is not empty. It has the node 2. So what we'll do is just pop that node and print it, and push it and print it, and then after that we'll just push both of its children. So now we'll have 1 and 4, and this is how the order continues. We'll just keep popping the elements of the queue and just and pushing both of its children down, and just continue from there. So again, when we go to 6, we see that it doesn't really have any children. So we just return, and then and this is how it basically continues. So I think you have the general idea. I'll just complete the code now. Print temp.data q.push root left. Okay, again, obviously we have to see that. Oh wait, I'll just make it temp instead of root. If obviously we have to see that temp should not be null, because obviously then it doesn't really make sense. If it's not null, then we push the left node, and again, so yeah, this is basically the gist of what we do with this particular question. We'll just keep printing the element and just keep going over and over. Okay, next question, right? So what we have already covered the traversals. Now we'll just try going through a question. What, for example, what is the height of a tree? And so let's just take an example of this particular tree only that we have in front of us. So I'll just clear the screen. So height of a tree. So how we find the height of a tree is basically, like as I already said before, when we are dealing with trees questions, we have to think of recursion and think of breaking the problems down. So, for example, if we had just a tree of this size, right? If we just had a tree with a root node and we had no children, so obviously what we have to do is just see that if there is no children, we'll just say that the height is 0, right? Because it obviously is there is just one node. And if the question was like this. So what we do in these questions is just as I said, we try to break the problems down. So how we'll actually do is when we are at a particular node, we try finding what is the height of the left subtree and then what is the height of the right subtree. So for example, if there is this is a whole subtree, right? 2, 1, 4, and 7. This is the whole left subtree of the root 5 of the node 5, and then 3 and 6 is the whole subtree of the node right subtree of the node 5. So what we have to do is basically just see that whenever we are at a particular node, the height till that point would be whatever the height of the left subtree is, maximum whatever the height of the left subtree is and the right subtree is, and add 1. So how we'll actually deal with this particular question. So if I write a program and find height node star root. If again when we are at the root node, obviously the if it's null, for example, if there is basically no node, we'll just return -1. So that this we are doing because obviously when we are at just have one node in a tree, it's obviously it's left subtree and right subtree would both have null, right? So we'll just keep this check and return -1 whenever we see this problem. And then what we can do is return max of find height. So this is basically the entirety of the code, right? So this is sort of interesting that recursion, something some of the most problematic questions or some of the things that really are difficult to grasp could be solved in a couple of lines because things are often repeating themselves. For as I already said in question, for example, if we take the tree, if we take the if we take the root node as 2, then we have this whole left subtree with with the nodes 1 and 7, and we have the right subtree as just node 4. And again, we are doing the same operations over here, and we are doing basically the same operation for every single node. So let's just try to dry run this code. So first, what happens in this particular code is we'll obviously start with the root node, which is 5. So we'll go to the left subtree. Because this is like the find height root of left. So again, we go to the we have our stack, right? So we are at we'll go to the root 2, and we again see that the root is obviously the node is 2 right now, so it's not null. And then we go to the left subtree of the node 2. So now we'll actually be at the node 1, and for the 1, there's basically the same thing. It's just not null. And again, after null, we actually see that our root node is null. So we'll just return -1. So we have the for the node 1, we have our left height. Left height is equal to -1, and we have it. And then we'll actually go finding the right height of of the node 1. Then we go onto the right subtree, which is max height root of right. And we see that we have the node 7. So our just node is 7 right now. And then obviously the left subtree and the right subtree of the node 7 is just again null. So for 7, we have the both left h is equal to -1 and right h is again equal to -1. And then our code basically says that what we have to return is the max of -1, -1 plus 1. So basically from the 7, we'll actually be returning 0. So for the node 1, our right height would actually be 0. And again, we do the same operations. So we have to go find the max of -1 and 0, which is 0, and then we'll return 1. So for the 2, so this is basically how all the things go. For 2, we have the height as, so basically what we have done is for the node 7, we'll have our height is equal to 0. For the node 1, we'll have our height is equal to 1. And then for the node 2, again, it's 2. And then for 5, it would be the maximum of left and right. So the left height is basically just 2, and then the right is just 1. So again, the final height would come out to be 3, which is the path from the 5 to 1 and 7. So this is the height traversal of a tree. And if anything, again, I'm reiterating myself. If anything wasn't clear enough, you are free to ask me questions, because I may go over things slightly faster, depending upon, obviously it varies from person to person, right? And there is not a free lunch theorem in DSA. It just takes different times and different things for things to click for different people. So let's just move on to another question, which is sum of all nodes. So what exactly is this question is, we have to find the sum of all the particular nodes. So again, you'll see that we are actually doing something similar. For example, when we are actually at a particular node, what we have to do is find the sum of all the nodes that are in its left subtree, and then we have to find the sum of all the nodes that are in its right subtree. And again, we have to add those, and then obviously add the data that we have at a particular node as well. For example, let's just take a basic case. If I had just this particular case, the answer would be like, first we'll go to the left subtree of 5, which is 2. So basically the left subtree of 5 just has one node. So our what we'll be returning from the left subtree would be 2, and then what we'll be returning from the right subtree would be 3. So and then we'll actually be returning the sum of everything that we could find from the left subtree and the right subtree. So we'll sort of be returning 2 plus 3, which is 5, and then again we have our root node. So the answer here would be 10. And let's just make it slightly more complex. So again, in this particular case, what we'll do is first we have the root node, which is 5. So we try finding the sum of all the nodes present in its left, and then we try finding out sum of all the nodes present in its right subtree. So obviously, since there is just one node in the left subtree, we'll be returning 2 from there, and then there are like more levels in the right subtree of 5, right? So first, what we have to do is return whatever the sum of the right subtree of all the trees and all the subtrees in the node, which is 3. So we have to calculate if 3 has any left subtree. So we don't really have any left subtree for the node 5 or node 3. So we'll just return 0 from that because it's null. And then we'll actually go on to the right subtree of 3 and see that it has node 6. So we'll just be returning 6 from here. And then from the 3, again, we'll just return whatever the sum of the left subtree is, which is 0, and then whatever the sum of the right subtree is, which is 6, and the node itself, which is 0 plus 6 plus 3. So we'll be returning 9 from here. And for the left subtree of 5, we've already covered, but again, the sum over there is just 0. The left subtree is 0. The right subtree is 0, and then the node is just the value of the node is just 2. So we'll be returning basically 0 plus 0 plus 0 plus 0 plus 2, which is 2. And just wait. So we are returning 9 from the right subtree of 5, and we are returning 2 from the left subtree of 5. So over here, the final sum would be again what we could get from the left subtree of 5, which is 2, and then what we could get from the right subtree of 5, which is 9, and then the node itself, so which is again 5. So the sum here would be just 16, which matches with what we should expect. So 5 plus 2 is 7, 7 plus 3 is 10, then it's 16. So this is the basically general approach. So if you were to break the problem down, the logic is just extremely simple. So what we for every node, what we are actually doing is find sum of root left and adding it to find sum root right, and then root. So this is the crux of the logic that we have. Now, if you were to actually write the code of this particular sum, then and find some obviously if the root the base condition would be when we don't really have any nodes, or if the node is null. So for that, we'll just have to return 0 in that particular case, right? So again, this is just all the code that we have. This would give you the desired result. So I think if nobody really has any questions, we can move forward to the next question which we have. So what we can do is just try looking into the diameter. This is like a slightly more complex or more difficult question, if you could say. I mean, as I said, I'm just covering some of the most asked interview questions because these are trees are generally asked in your competitive coding examinations. So the only sort of trees that are generally asked in your competitive exams or a competitive coding is just segment trees, and segment trees is a lot of work, and you have to cover a lot of things to actually go over them. So again, the next one is the diameter of the tree. So what we actually mean by, let's just go what we actually mean by the diameter of a tree. So the diameter of tree is basically the largest distance between any two particular nodes. For example, if you were to cover, if you're just taking the example of this, if this particular tree, right? So the maximum distance that you can see is the path that we have from 7 to 1 to 2 to 5 to 3 to 6, and our answer would be in that particular case, the diameter would be 7 to 1, 1 to 2, 2 to 5, 5 to 3, 3 to 6. So that is just 5. Now we have to think all the scenarios that can basically arise in when we are finding the diameter of the tree, because and see all the different situations and try to think how we'll handle that. So let's just so what happens? Okay. So in general, what you'll observe is there are like 3 possible cases that can take place. I'll just say it's LS, so what it just means a left subtree, and then there is the right subtree. So the 3 possible cases that you can think of are basically when we are actually crossing over. So what I mean by crossing over or actually going through a whole path is when our final answer both has nodes in the left subtree and in the right subtree, and then we are actually going through the root. So this is the example that I basically covered in the tree that I have in front of you. So in this case that you can see, right, we're actually going through we're actually covering the left subtree, and we're going through the root, and then we're also going to right subtree. So this particular node is basically, wait, I just see if I can switch to maybe sort of a whiteboard, which will be easier to explain. I mean, please bear with my handwriting, because obviously it's like I don't really have a stylus in front of me, so it's like sort of difficult to draw things. But again, what I meant with the three scenarios, and when we are going through the whole path. So this is the path we are actually covering the left subtree, the right subtree, and the root node. So we are actually covering all of the edges and all the scenarios. And then the other case that I could say, this is one of the case that we can see. And then the other case would be, for example, when we have like a lot of nodes in the left subtree, and then we don't really have any nodes in the right subtree. So in that particular scenario, it is possible that our whole answer can actually be covered by all the nodes that we have in the left subtree, and answer is just the height of the subtree over here. And then obviously the third case is just a mirror of this. So when we have all the nodes in the right subtree and don't have anything in the left subtree. So if I give you an example of that, it could be okay. So again, so in this particular case, this is the second case that I was mentioning. The actually diameter would be, we won't actually, maybe, yes, I should probably add one more node over here. So again, in this particular question, we won't be going through the root node of 5. We'll just be going through all the nodes in the left subtree of 5. So the answer would be 7 to 3, 3 to 2, 2 to 1, 1 to 4, and 4 to 8. Because in this particular scenario, our diameter would be 1, 2, 3, 4, 5. So it would be 5. Wait, maybe I should add another node so that it's more clear. It's clearer. So yeah, this is generally what's happening. The answer here would be 6, because it's 7 to 3, 3 to 2, 2 to 1, 1 to 4, 4 to 8, 8 to 9. And again, it's just 6. And then if we take the scenario of the other tree, which is 7 to 3, 3 to 2, 2 to 1, 1 to 5, and 5 to 6, that's 5. So obviously our diameter is the maximum distance between any two particular nodes. So the answer would be 6. So I think we have covered all the cases in this particular. Now how we approach the problem is like when we have actually seen all the scenarios. So we see that there are like 3 possible scenarios. Like one is when we are actually, our answer is the diameter. So our final answer is our diameter of the left subtree of a particular node. So which was the second case that we have, which is this particular case when we have the diameter of the left subtree of 5, which we already have seen was 6. And then it could be, again, we have to find the maximum of all these things, right? So it could be like the diameter of the right subtree of a particular node, which would just be the mirror scenario of the question of the thing that we were already covering, and then the final answer would be when we have when there is like a straight the first case, right? So this is just the height of the left subtree and the height of the right subtree. So again, if we are just talking about this particular case for the node 5. We have the height of the left subtree of 5, which is 3, and we have the height of the right subtree of 5, which is 2. So we'll just say it's height of 2 left plus height of 2 right. So these are basically all the scenarios that we have. So I think we've covered all the scenarios. So, I mean, I don't really know if I went fast or, I mean, I tried to explain it as much as I could without, without the use of any whiteboard or any sort of a thing. So if I were to write the code of this particular question, I think it would be just sort of, obviously we have already written the function of how to find the height of a particular tree, right? So again, so what we'll do is, this is again just a pseudo code in diameter of I mean, if you want the actual question, the code of all the questions that I've written and the actual code of all these, you can just reach out to me later. I'd be happy to provide you with the answers. Now, if root is equal to null, then obviously we have to return 0. So, I mean, I think we are already jumping over the time, but I think this is sort of like clear enough. So what we so if I just try run the code quickly, we'll actually just keep on going till we have the root, right? So the last node we'll see would be 7, and then we'll see that the left subtree and the right subtree of 7 are both null. So we'll just return 0 from that, and then so we have the diameter of the root of left as 0, and the diameter of root of right as 0, and then the height of both of these trees would be 0 as well. So the answer that we'll have on the node 7 would be 0. And then we'll actually go on to the node 3. We'll see that the diameter that we are actually receiving from the left would be 0, and then what we are receiving from the right again would be 0, and then the height would be the root of left plus root of right plus 1 right. So the height here would be again. And now the height of the left subtree of 3 would be 1, and the height of the right subtree of 3 would be 0. So the final answer that we would have would be max of 0, 0, and 3. So our final answer till here would be 1. Maybe I'll try writing it to the right side. It would be 1 over here, and then we go on to the root node 2. Then again, we will see that the diameter of the root of left would be 1. The diameter of the root of right would be 0, and then the height would be again the height of the left subtree, which would be again which would now be 2, and then height of the right subtree, which would be 0. So our final answer would be again max of 1, 0, and 2, which would be 2, and then for 1 it would be 3. 1 it would be actually for 1 we have the it would be maximum what we have from the left. So we have the maximum of diameter of left, which we'll receive from the node 2, which would be 2, and then the answer that we'll receive from the right subtree. So the diameter that we'll receive from the right subtree would be 3, which will be actually 2, which is just similar to the what we received from the left subtree. So again, it would be 2, and then it would be max of the height of the left subtree and the right subtree. So it would be 3 plus 3. So it would be 3 plus 3. So the max will return the maximum of all of these values. So we'll end up returning 6 over here. So now we have so now we have the node 5. So for the node 5, again, what we have to do is, again, this is like our main case. We'll actually find the answer that we found on the left subtree. So the answer that we found on the left subtree was 6, and then the answer that will come from the right subtree would be just 0, 1, and then we have and the final thing would be the height of the left subtree and the height of the right subtree. So the height of the left subtree would be 4, and the height of the right subtree would be 1. So it would be the maximum of 6, 0, and 5. So we'll just return our final answer as 6. So which would be the final answer. So I think that's all for binary trees. Now I'll just quickly just go through the VSTs extremely quickly. So the VSTs are just binary trees which are actually which have some sort of an order in it. So what I mean by order is that actually they're sorted. So if you're talking about a particular VST, what happens is that the left value or the left node of a particular the left node in a particular tree would always be lower than its parent, and the right node will always be higher than its parent. So this is an example of a VST that I've already shared. So as you can see, if you're considering the node 5, all the values that are in its left subtree, right, which are 3, 1, 4, and 2, are actually lower than 5. And then all the values in its right subtree, which are 7 and 9, are actually higher than the root. So for the node 5, we have the values, as you can see, all these values are smaller. And then for the node right subtree, all these values are higher. And same is the case for all the particular subtrees. So if I'm talking about the subtree with the root node as 3, then all the values in the left subtree of the node 3, which are 1 and 2, are smaller than 3, and all its the values in its right node is greater than 3. So again, that 4 is greater than 3, right? And this is similar for the right subtree of 5 as well, where the right subtree of 7 has a higher value. So 9 is greater than 7. And if we were to expand that, then maybe I can also add like maybe 6 to make it more. That covers all scenarios. So as you can see, again, in this particular case, we have the subtree with the node 7. The value is in its left subtree. We have the node 6, which is lower than 7. And then its right subtree, we have the node 9, which is greater than 7. So this is what a BST is in general. And then, okay. So what we can do is just write one quick code about how would we go about checking if a particular tree was a BST or not. So just take an example of the last tree that I made. So in this particular scenario, obviously you can see that this is not a BST because in the left subtree of 5, we have a value 7, which is actually greater than 5. So this is breaking its rule. And then its right subtree of 5, there is 3, which is again, which should have been greater for it to be a BST, but it's not. So obviously it's breaking the rule as well. So there's just one interesting thing about BSTs, right? Whenever we do an in-order traversal of BSTs, we actually get a sorted list. What I mean is that if we actually were to do an in-order traversal of this particular tree, it would be, again, in-order traversal is just first going to the left, then the data, then right. So the in-order traversal here would be just we keep going to the towards the left. So the last left node that we see is 1, and we can't really go any left. So we have already covered the left, and then we print the data. So that is 1, and then we go try and go to the right subtree of 1, which is 2. Again, 2 doesn't really have any left, so we print its data, and then we go to the right, which doesn't really have anything either. So now we are back to 3. We have already covered its the left subtree, and then we print whatever the data is. So it's 3, and then we go on to the right subtree. And this is how it basically continues. So it's sort of like an interesting observation. Yeah. At the in-order traversal is basically a sorted array of a VST. And now, if you were to check if a particular binary, if a binary tree was a VST or not, let's just quickly write its VST. It's the root. Okay, so one of the ways that we can actually check is just doing an order traversal and comparing that the values that the last value we saw was actually less than the value that we have right now. So this is one of the ways. And then another way that we can do is just, for example, when we are at the like this VST root and okay, so as I said, if you're at a particular node, all the values here should be less than in the left subtree, all the values should be the less than 5, right? So so our final answer could be return this VST root left, and then the left val and right val, what I mean by here is the interval that a particular value could lie between. So obviously, if we are actually going for the node 5 in its left subtree, the value could actually range from -infinity to 4 or -infinity to 5, right? So the left val would remain unchanged for the left subtree, and the right val would actually become the data of the root. And then again, we have to do something similar for to check if the right subtree is VST or not as well. So in the right subtree, we obviously see that all the values have to lie between. If we are taking the example of 5, it has to lie between 5 and infinity. So the left in this particular case, our left value would become the root data, and the right value would remain unchanged. And obviously, if this is basically what would happen in this particular scenario, and let's just write a basic check. So if the root of the data of a particular node has to be, as I said, it has to lie between the left val and the right val, right? So it has to be it has to be greater than left val, and has to be less than the right val. And if this is the condition that we actually break, so then obviously we'll have to return false. And then if root is null, we just return root. So this should basically cover BST. So I mean, I think the properties are clear. BST is just a sorted binary tree where the insertion, deletion, and searching could actually be done in log n complexity. I mean, log n. I think we can assume it to be log n, but it's actually just O of h, and the height in general would be log of n, because when we are actually talking about BSTs, we just take the case that it will be. In terms of questions that are asked, we just take the case that it is actually height ordered or or balanced. Okay, so moving on to the last topic, again, I'll just try to quickly go over this. So at the last, we have a graph. So graphs are basically, again, another nonlinear data structure. It's just like sort of a network. And I mean, why do we need it? I mean, interviews, the graphs are actually pretty often asked in interviews. It's like one of the favorite questions that the interviews have. I mean, in general, in the interviews that I've seen, people just ask a basic BFS or DFS. BFS is just a breadth first search, and the DFS is a depth first search. They don't really go any deeper than that. So, I mean, if you just know a BFS, DFS, and this topological sort, you should be actually good for the interviews of most of the companies that we have. Obviously, there are some sort of exceptions, but yeah, this should cover it. And then if you're actually talking about the competitive, your competitive contest and everything, again, there is like a lot of things that in the graphs that we actually have to cover and we have to go through. And actually also in the interviews, it's also obviously your diecast or the shortest path, and these questions are often regularly asked as well. But again, they're just like small modifications in your traversal algorithms, which are BFS and DFS. So why do we actually need graphs? So graphs are basically it's like a really close to us, right? We see graphs or the structures all over us. So if you're talking about the social networks, they're obviously like some sort of some sort of a relations between different people, right? So graphs are generally used to annotate these relations that two particular objects have, and it's like the best way to cover those. And then obviously we have the Google Maps where the graphs are used really often, and then in the supply chain management, if you are talking about this. And then one other thing that I wanted to add was that the questions for the graphs that we generally see, some of them, for example, the connections or if we are actually talking about the connections or the components, it can also be solved by DSUs. So DSUs are your disjoint set units. So maybe you can actually look into them. Obviously, we don't really have to have the time to cover those. And then there are different ways to talk about graphs to represent them. So one of the adjacency metrics, which is actually even though in real life applications this isn't what we use, but in competitive exams and in competitive contests and in actually interviews, the adjacency matrix would suffice, and most of the questions actually require us to use adjacency matrix. What I mean by adjacency matrix, if there is a one particular graph that we have, for example, let's just draw a graph. So this is like one of the graphs that we can think. This could be node 1, 2, 3, 4, 5. So this is an example of a graph that we have. These are the graphs are denoted by our edges and vertices. So in this particular graph, we have 5 vertices, which are 1, 2, 3, and 4, and 5. And then we have these edges, which are connecting 1, 2, 1, 3. And so we have 6 edges between them. And if you're actually talking about connected graphs where the maximum, the maximum edges that we can have, which are is NC2. So that is NC2. So that is just n into n minus 1 by 2. And the least amount of edges that we can have so that every single node is reachable could be n minus 1, which is just another fancy word of saying an array. So this is generally how the graphs are represented. They are just edges and vertices, and how we represent them in adjacency matrix is just we create a mapping for all the edges that we have. So in this particular case, we have like 5 edges, right? 4, 5. 1, 2, 3, 4, 5. So if we see that there is like an edge between there, not actually covering where one particular node can be reached by itself, right? So this would just mark all of these as 0. Because there is no edge from one vertex to itself. And then we signify that if a particular two particular vertices are connected, then we mark them as 1. So there is one edge between 1 and 2. So we mark it as 1. Then there is also another edge between 1 and 3. So again, we mark it. And then there is obviously not an edge. There's also an edge between 1 and 4. So we mark it as 1. And then there is no edge between 1 and 5. So we mark it as 0. And this is how it basically continues. This is just a representation of an adjacency matrix where we signify that if two particular nodes are actually connected, we signify them by 1, and if they aren't connected, we just represent them by 0. Obviously, in this special case, when there is some sort of weight attached, or there's some sort of weight between two particular edges, instead of marking it as 0 and 1, we can actually represent them by a numerical value. So next is our edges and vertices, where basically we just have all the edges. So we have edge 1, and then we can go over and see all the edges that let's just cover it adjacency list, because edges and vertices aren't really important. So, and what happens in adjacency list is just we have a list corresponding to every single vertex, and we have all the nodes which are actually connected. So if we have, so what we have in an adjacency list, it's just all the edges, all the vertices that it's connected to. So one is connected to 2, one is connected to 3, one is connected to 4. So we won't really have any mapping between 1 and 5. So the advantages of the adjacency list is obviously it takes less space, because we don't really map the relations where we don't really have any edges. However, for the adjacency matrix, the space complexity is O of n square, and for adjacency lists, it's just O of E. So yeah, that is that. So now we have the ways to represent the graphs down, and then obviously there are two sort of traversals, which are the breadth first search and the depth first search. So what happens in a breadth first search is obviously we'll start from one particular node, and we'll see all the nodes, all the edges, all the vertices that we are connected to that particular vertex, and then we just go through them. So for example, it just, again, when I said that, whenever you think of breadth first search, think of some sort of queue, because these are the, in breadth first search, they are the ones most often used. Yeah, I mean, I don't really have the program to cover, time to cover the code and write the code as well. So I think you can just go through them, go through the BFS and the DFS yourself. So, I mean, I think that's it for the session. I'm sorry if I rushed through some things, or if I didn't really cover everything that you wanted to be covered in a bit more depth. But yeah.
Okay, sir. So here are a few questions.
Okay.
Can you give us a glimpse of your preparation for ICPC 17 and 19, and what did you do differently for the same, especially in your second year?
Okay, so first, basically, I just stopped sharing my screen and stopped presenting. So talking about ICPC 2017, where it was my first time, obviously I had one of the first tasks that we have to do is identify that where we are, identify and evaluate where we stand, and then obviously you have to find your teammates which are in line with you, and you can actually collaborate with them and can go through different things. So once we had the team down and everything was sorted, we just went through and covered some of the questions. So again, the preparation was just solving as much questions as you possibly could, covering all the things horizontally and as well as vertically. So I was participating regularly in your code chef contest and in your code forces contest. So I had so obviously that is like a prerequisite for you to do well in any competitive coding sort of a contest. And then again in 2017, we weren't really the favorites or anything. I mean, we were in our second years, and it hadn't been really, because I didn't really start coding till I was in my second semester. So I just started it then. So no one was expecting us to, do as well as we did. So it was sort of easier, that we didn't really have any pressure on, and just we could just do our best and see what happens. And then actually in third year was the one I'd say I was the most prepared, but it sort of backfired. And obviously there is always some sort of a luck attached to different contests, right? So I mean, you could be stuck at the one of the basic, or the one of the most easiest questions. So luck also plays a huge role. I mean, so obviously because of that, and maybe my preparation was lacking, I didn't make it in my third year. And then in fourth year again, we tried to resolve the mistakes that we made in the last contest, and again started coding, and started again practicing in your various online questions. So we were participating regularly in the CodeShare contest, and then in your Code Forces contest. And in addition to that, we were also obviously went through the questions that were asked in the last ICPC rounds. And then we, before the ICPC, 1 month before ICPC, we were actually solving these questions as a team. So we could actually play to our strength and identify the weaknesses. So yeah, that's it.
Okay, sir, that's great. So the second question is, sir, what is more important for cracking coding interviews, CP or DSA?
Sorry, could you come again?
Sir, what is more important for cracking coding interviews, CP or DSA?
I mean, for cracking coding interviews, I would say CP is just a completely different avenue. You don't really have to do CP in much, because obviously, as I said, in interviews, the questions that you're asked are completely different to CP. But obviously, CP helps in that case that you are actually able to debug and see things more clearly. It provides you a better perspective, but again, it's like completely different. For example, as I already said, if we're just taking the example of trees, in CP, absolutely no one would ask you any BST question or a binary tree question. There's just no chance of that coming. Even linked lists. I mean, no one would ask you any linked questions covered by linked lists. So the question that we are generally asked over there, if we're talking about trees, are the segment trees or the Fenwick trees, and with some sort of a lazy propagation or things like that. So again, it's like completely different field. If you're actually preparing for an interview, to crack an interview, I think the best course of action would be to just practice on LeetCode or interview bit, and refrain from going for your Code Forces or CodeShare.
Okay, sir. Sir, could you please list out some of the most important topics specifically related to Flipkart interviews?
Okay. I mean, actually, the questions in Flipkart that I saw were, I took the interview of several different companies when I decided to join Flipkart. So in Flipkart, I would say it was slightly more DS oriented than others. For example, if I'm talking about Goldman Sachs or Amazon's and the others, it actually covered different perspective, different things as well. But for Flipkart, one of the main things was DSA. So and then there was some sort of a design question where we had to just they just gave us a problem statement, and we had to go through. We had to prepare a design for it and code it. So for Flipkart interviews, again, the topics that I would say are the most important are again, it's trees. So trees, what I mean by trees is just the binary trees and your VSTs. Then obviously linked list, and then actually DPS is also asked often. So I was asked a couple of questions in DP as well. So even in DP, the questions are like sort of like medium or easy medium. So they don't really ask very tough questions. And then for every sort of interview, obviously the strings are asked several times. So the strings and the arrays are also really important as well.
Okay, sir. Sir, I think that's it for today's session. We would like to thank ARPIT sir for such an insightful and enriching session. Before we sign off, there is an announcement for the audience. We are excited to share that our very first open source project, Code CROSSROAD, is live. You can find the link for the same in description and contribute to it. Stay tuned with the Linktree handle for all the updates. and all the links have been provided in the description below. Thank you everyone for joining us today. Have a good day.